F1, 2 due to mass number 1. And they're going to be equal and opposite. Equal in magnitude, opposite in the direction. Their magnitudes, F21 is equal to F1, 2. And the formula for this, if you remember from physics, is G M1, M2, the product of the masses, times this magic gravitational constant, which is 6.672 times 10 to the negative 11th, and that's units of Newton meter squared per kilogram squared. And then divided by r squared. This is a 1 over r squared law, like so many other field equations in physics. So, that's how we start. Now, Newton also came up with some pretty sharp things to say about the motion of objects. So Newton's law of motion, one of the bedrock concepts in physics, F equals ma, force is equal to a mass times an acceleration. High school, you knew here at bedrock physics, typical English teacher put this on the board and called it Newtonian mechanics, and one of the students asked, raised a hand, and they said, well, could you explain what this means again? And the professor kind of looked at it and he said, well, you see, F equals ma. I'm not sure you can really give a better description of it, right? This is how it works. This is the world. And so it kind of cracked up the class a little bit, but F equals ma. And the interesting thing about this is that even though we kind of present these as two completely different formulations, Newton's law of gravitation and Newton's law of motion, it's interesting that they use the exact same masses in one another, and that if you equate them, one of the masses drops out, the mass of the moving object. And so, even at this point in time, this was actually one of the hints of the idea of general relativity. It just so happens that these masses are the same, and they always drop out when you put them together. And so that the object is left with just this intrinsic property of space and its own mass, or the mass of the object nearby that is influencing its motion. So let's go ahead and work through that quick exercise. If every force makes an acceleration, then let's say I want to study the movement of mass 1 in this system that I've drawn over there. If that's true, then m1 times a1, acceleration of 1 times mass of 1, would be equal to g m1, m2, r squared. Of course, the masses cancel, and the acceleration of body 1 is only due to the presence of the mass of the object number 2. And that's a profoundly simple result. Now, we're engineers, so we have to do this rigorously. I'm doing everything in scalars at this point. To really understand orbital mechanics, we're going to have to move into a vector representation. And so here's the convention that we're going to use to talk about orbits in this class. We're going to have an origin. And it is more convenient at this point to work in the cylindrical coordinate system instead of the Cartesian coordinate system. So instead of describing an orbit in terms of x and y, I'm going to use r and theta. And that is actually the physics and mathematics convention, not the electrical engineering convention, because most of this stuff comes out of physics and mathematics books. Electrical engineers haven't written that much about orbital mechanics. If we were doing the cylindrical coordinate system, it would be, what? Rho and v. That's how electromagnetics engineers talk about these things. So, this is r, and the angle that you would make with what normally would be the x-axis in the Cartesian coordinate system, that's what I'm going to call theta. So the point in space, if I describe it as r and theta, that will describe in a two-dimensional space the trajectory of my orbit. R is a function of time, and theta is a function of time. Okay. Now, everything that I'm going to draw on the board is going to be two-dimensional, without loss of generality, right? Because if I have a planet and I got a satellite orbiting around it, there is a plane that's going to contain the centroid of that planet and all the points on the orbits. I may have to tilt the plane and do some crazy twisting with it, but there's always a plane that I can normalize the problem, and that really simplifies everything, the math of the analysis. In fact, when you do homework number 1, which I'll assign probably early next week, what you'll be doing is doing a 2D code, and then when you're finished tracing out the orbit, you're going to twist and tilt it up until it's inclined, and then actually do a sky track or a ground track of the orbit, the track that it makes along the Earth, and then the track that it makes across the sky, which is ultimately where a lot of this analysis is going. We're electrical engineers. We want to be able to point antennas to our satellites. How are we going to know where to point them if we don't understand our orbital mechanics? And so that's one of the key questions that we want to ask at the end of this. So don't get too bogged down with the mathematics. There's light at the end of the tunnel. Okay, so my trajectory is a pair of coordinates, r and theta, and they're going to change as a function of time. They're going to be time-varying functions. And then from here on out, I'll probably just drop the parentheses t, because we all know that they're going to change with respect to time. Now, mathematically speaking, not talking any physics now, just pure mathematics. If you pick up your old dynamics book from your freshman year or sophomore year, for those of you that even take dynamics anymore, in about there's all these formulas that tell you how to get velocity from a position vector in any arbitrary coordinate system, any acceleration. And I'm just going to give you what the back of the book says for the cylindrical coordinate system. Velocity vector, in terms of r and theta, is given by r dot, r hat, the unit vector that always points away from the origin, plus r theta dot, theta hat. That's the orthogonal unit vector, theta hat, that always points in the direction of increasing theta. The dot, of course, is the first derivative with respect to time. And you'll notice that we didn't just take r dot, stick it on the r, and theta dot, stick it on the theta. That's something that my undergrads make a mistake of whenever they're doing vector operations in my electromagnetics class. You can get away with that kind of horseplay in Cartesian coordinate systems because x hat and y hat and z hat are fixed with respect to your points of observation. No matter where you go in life, in a Cartesian coordinate system, x, y, and z always point the same direction. So the constants. One of the double-edged sword about when you move into coordinate systems like the spherical coordinate system or the cylindrical coordinate system or whatever crazy coordinate system some mad PhD has invented to solve a problem and escape his PhD program, those coordinate systems are formulated in a way to simplify some geometrical aspects, but they often complicate other aspects. They almost always complicate taking derivatives, because if I take the derivative of r on the r hat and theta here, these r's and thetas change depending on my points of observation. So I can't just take the derivative. It's not even dimensionally correct. Like theta dot is radians per second. I need something that has units of meters per second in order to be a bona fide velocity. And so that's why I gotta multiply those two things. Acceleration is even uglier. If you want to take the next derivative with respect to space, and you look in the back of your dynamics textbook, you get this crazy expression. R double dot, second time derivative with respect to time, of R with respect to time, minus R theta dot squared, stick it on the R hat, and then finally, that's all on just the R hat, then on the theta hat, you get this component, R theta double dot, second derivative of theta with respect to time, plus 2 R dot theta dot on the theta hat unit vector. Okay. So that's it. I don't think I made any boo-boos. Now, how do we use this to figure out what the orbit should be? Okay, so going back over here, let's make a more formal treatment. My acceleration vector is going to be equal to minus GMP over r squared, stick it on the r hat, plus 0, theta hat. How did I get this? Okay, first of all, we're gonna leave the textbook physics world and enter into satellite communications. What am I orbiting? Flatness, usually. I just call this M sub p. That's gonna be the mass of the second object. Now it's the mass of the planet that's exerting gravitational forces on the spacecraft. There's your Newtonian constant r squared. Minus, it always points towards the origin. We are going to place our planet at the origin. The centroid of the planet is at the origin. Then I have an r and a theta that traces out a trajectory around there, and it has to follow this equation. Newton's force always points inward, so I conveniently align myself with the cylindrical coordinate system. There are no tangential forces, so I'm going to assign that equal to 0. And this gives me a great way to solve the system now, because this is the mathematical definition of my acceleration vector. All I have to do is equate the r hat components and the theta hat components. So I have basically two coupled differential equations now that describe the motion of this system. We have r double dot theta dot squared equals minus GMP r squared. That's equation number 1. And then finally r double dot 2r dot theta dot. The sum of those is equal to 0. Questions so far? So really, the first week or so of class is just solving that system right there. It's pretty simple. And then also describing how does real life deviate from this. Because real life is never this clean, unfortunately. I think orbital mechanics is about as clean as anything gets scientifically to solving a pristine differential equation system. But even there are some irregularities. Now we're going to start by solving it for the simplest possible system, okay? The simplest possible system, the circular orbit. The circular orbit. For circular orbits, if we are to have a circular orbit then we can derive some pretty simple condition for what that orbit has to satisfy based on this dynamic set of equations. So, well, let's go ahead and take a look right so we have them up. R dot, double dot. If R is a constant, every time you see R